So I'm going to do one example problem of the next set of problems. I mean, it's really not too different than the kind of problems we did in heat. But we learned, so the last thing we were talking about was heat transfer. And we learned that you know, the three types of heat transfer, there's conduction, and we learned a formula for Q dot. Radiation, we learned a formula for Q dot. And convection, we learned a formula for Q dot. And the form that we've been using mostly for the first law of thermodynamics says the change in the total energy, the change in the energy properties, is equal to Q minus W. But if we're dealing with heat transfer, then, you know, we have the heat transfer equations telling us the rate at which energy is entering the system through heat. And so we'd like a form that fits that for the first law. And so together, these suggest that we want a differential form of the first law. And that is the time rate of change of the energy is equal to the rate at which energy is entering the system through heat. That's what we're calling Q dot, minus the rate at which work is being done by the system. You know, energy is leaving the system through work. Okay, so this is the differential form of the first law. And when will you use the differential form as opposed to the form that we started with? The most likely signal is that you're dealing with some kind of heat transfer. If you have heat transfer, you're going to come up with an amount of heat using your Q dot equations, and then the way you'll need to go is the differential form. And one thing that we're going to use a lot is in steady state, that means all properties of the system stay the same. So if you're using the standard, you know, our starting form of the first law, delta E is equal to 0, and that's equal to the change in kinetic energy. That's equal to the change in potential energy, and that's equal to the change in the internal energy. And if you're using the differential form, then dE dt is equal to 0, and that's equal to d dt of the kinetic energy. That's equal to d dt of the potential energy, and that's equal to du dt. All right, so here's an example of the kind of problem that you'll be doing in the next set of problems that I assign. These are the problems that are under the heading differential form of the first law. So, okay, let's say that you have a microchip and it's embedded in a surface. So this is a microchip embedded in another material. And to cool it down, a coolant is sent flowing over the top. So only the top surface of this microchip is exposed to the coolant. The rest is embedded in this surface. Only the top surface of the chip touches the coolant. And the area of the top is 5 millimeters by 5 millimeters. So what type of heat transfer are we talking about here? That's convection, yeah, because the fluid flow, the fluid's moving across. So it's actually, so heat is being transferred from the top of the chip to the coolant, and then the coolant particles are physically moving that heat away. It's not, that heat isn't transferring away from the chip particle to particle through energy. Those particles themselves are actually moving away. So this is convection. And through experiment, we've learned that H is equal to, that's the constant for heat transfer from convection. H is equal to 150 watts per meter squared Kelvin. The coolant temperature is 20 degrees Celsius. And the electric power going to the chip, so that's an electric power input to the chip, is 0.225 watts, so that's joules per second. So if the chip is in steady state, what's the temperature of the chip surface? Well, this is convection. The formula for heat transfer from convection is Q dot is equal to H times the surface area that's in contact with the flow times the temperature of the body minus the temperature of the fluid. The area is 5 times 10 to the minus third squared. So that's 25 times 10 to the minus 6 meters squared. So Q dot is equal to 150 times 25 times 10 to the minus 6 times 20. Oh, I have this backwards. Trying to calculate the temperature of the body. So PB minus 20 degrees Celsius. The electric power is 0.225 watts. So how's that going to come into this equation? So watts, power is the time derivative of the work. So power is the time derivative of work. And so we have to think about if we're going to transfer this into W dot for the equation, is that electric power adding energy to our system? Well, what's our system? The chip is our system, so is that electric power adding energy to the chip or taking it away? It's adding it to the chip, so does that count as W dot positive or W dot negative? Negative. So W dot is equal to negative 0.225 watts. And we have to think about the sign of this Q dot too. The formula gives it to us in sort of a, it gives it to us in a sign convention that doesn't reflect the sign convention for the first law. Is the temperature of the body going to be higher or lower than the fluid? It's going to be higher. We're using that to cool it down. So this is going to be positive. Does it make sense that convection is adding? So if we leave it positive like that, does it make sense that this convection is adding energy to the chip? No. Energy is being removed from the chip through heat transfer. And so we're going to make that negative. So the differential form of the first law says dE dt is equal to Q dot minus W dot. This goes away because it's steady state. And so 0 is equal to, now we have this form of Q dot. So we got that it's negative. 150 times 25. So we can write this as negative 0.00375 TB plus 0.075 plus 0.075. Okay. So negative 0.00375 TB plus 0.075 minus, and now our W dot is negative, so this is minus negative 0.225. now we have one equation for one unknown, so we can solve for the temperature of the body. And if you solve that equation, you get PB is equal to 80 degrees Celsius. Any questions about any of that? You know, like with a lot of this stuff, like the easiest place to make mistakes is with the sign convention for the first law. That's the biggest single thing that you have to worry about in this whole class is the sign convention. It's going to be true when we get to the second law too. So, any other questions about that? Okay. I'll give you some problems related to that for next time. So the next topic that we're going to go into, new topic. This is properties of compressible substances. And a simple compressible, well, the basic idea, what we're trying to do in this whole section is we're trying to find mathematical relationships between properties. And so, like, how would that come up in a problem? When would you want to know a mathematical relationship between a handful of properties? Well, an example would be, you know, this is talking about a microchip, which isn't what we're going to be talking about. But imagine that our system was, well, imagine that we could do this for the microchip. What if, because of complexity of the fluid flow or whatever, we didn't know what the temperature, and we had no way to measure the temperature of the coolant as it flowed across that chip? You know, we wouldn't be able to do the problem the way we did it because our formula for convection required knowing one of those two temperatures. But what if instead we were able to measure the pressure in that fluid or the specific volume of that coolant as it went across? If we knew relationships between the specific volume and or the pressure and or the temperature at the state that it was in, we could use the stuff that we knew to calculate the temperature that we needed for that convection heat. Okay, so there are going to be just a lot of times where we have ways to calculate some of these properties at a state, not all of them. And in the cases that we'll be interested in, we won't directly be able to calculate the properties that we need, but because of relationships between properties, we'll be able to, you know, use another relationship to, in this case, calculate temperature. Okay. Think of the ideal gas law. That so think of the ideal gas law that says, in the form that we're going to use, the pressure times the specific volume is equal to a constant R times the temperature. In our form, this constant R is going to be specific for the material we're using. That's not the universal gas constant. But this is a mathematical relationship between pressure, volume, and temperature. And so if you know any two of those, you can calculate the other one. Okay, a simple compressible substance is any material that's homogeneous and unaffected by electrical and magnetic fields. And this will cover every material that we're going to talk about in this class. So any kind of engineering material that we're talking about in a liquid or a vapor phase is going to be a simple compressible substance. In this class. And the nice thing about simple compressible substances, so for any simple compressible substance, two properties is enough. So two properties out of pressure, specific volume, and temperature is enough to specify the entire state. Therefore, if you know two of those properties, you can find all the other properties at the state. Okay, and what are those properties? So, for example, if you know all these, you can calculate lowercase u. That's the specific internal energy. That's a property. Bless you. You can calculate, let's see, what else have we talked about so far? You can calculate a few things that we haven't talked about at all. This is called the enthalpy, the specific enthalpy. Lowercase s is the specific entropy. Now, how to do these calculations, let me put these in parentheses because we haven't talked about those. But how to do those calculations isn't super simple, but those calculations can be done. And a lot of times, for most of this class, we're going to get that information out of tables where somebody else has already done the complicated calculations, tabulated it. And so we can just go across a row and read off all the different properties that match the ones we know. by the way, that specific internal energy, well, all of these specific properties are per kilogram. So this is the internal energy of the gas or liquid that we're dealing with per kilogram. This is, yeah, all of those are per kilogram. Okay, so relationships between between pressure, specific volume, and temperature can be represented by a 3D surface that's called the PVT space. And so, you know, in theory, this one picture gives you all the information you need, but there's no way to read careful numeric values off of it. Let me show you what it looks like. But that's not what I wanted to do. So insert picture, desktop. Okay. So that's what it looks like. And the idea of this, so remember, this is a surface, it's not a solid thing. And so the fact that it's a three-dimensional surface means if you specify any two of those three properties that are shown, pressure, volume, or temperature, specify any two, it'll give you the other one. It'll show you where that surface has to be in the other direction. Okay, so this is what the PVT surface looks like for most materials. And then let me show you what it looks like for water. Water is a little different than other ones. PVT water. Okay, so what's the difference between these two? The difference is here versus here. And it's related to the fact that most materials, when they go from the liquid phase to the solid phase, they contract if you keep the pressure constant. Water expands when it freezes. And so if you do a, if you look at a graph of the volume, keeping the pressure constant, so look at a graph of, like think of a slice of this as volume versus temperature, just at a single pressure value. This says that as the temperature goes down, so for this one constant pressure, as the temperature goes down, the volume that goes backwards. So temperature gas to liquid. Oh, okay. So, So zero volume is over here. Sorry, I was reading the. It's a little confusing to read the slices because it's you think of this as like a origin. You know what I mean? But volume is increasing this way. So what happens is you keep a constant pressure and you decrease the temperature from a gas to a liquid. Now you're in a liquid, you decrease it more, and the specific volume goes down. Okay. Look at what happens if you're dealing with water. So now again, think of a specific pressure. You come across here, gas, liquid, and if you decrease the temperature more, you get a jump in the specific volume, and that has to do with the expanding that water does when you make ice. Okay, so this is water. Or other materials that expand on freezing. As I demonstrated, reading these three-dimensional curves is tricky. And so usually we look at projections of these. Usually we don't use the three-dimensional versions. Usually we use the different two-dimensional projections. Instead of the 3D surface. And so here's a picture of what the projections look like. So this is two of the three projections that it shows. The one we're actually going to use in a minute is the third one that it doesn't show here, but you get the idea of what the idea is. The one feature that that's going to be useful to keep in mind, the most important feature of the PVT surface is the part that's called the vapor dome. That is this thing. And if you look on it, imagine looking at it sort of front on. It looks like this. Okay, so this is the vapor dome. At the bottom is the triple line. So that's all the places on this surface where gas and liquid and solid can exist in equilibrium. On the left side, the boundary here is the saturated liquid. On the right side is saturated vapor. To the left of that saturated liquid line is all liquid. Well, until you go, if you go even farther to the left, you get solid. In this class, we're only concerned with liquids and vapors. Inside the vapor dome is a liquid vapor mixture. And to the right of the dome is superheated vapor. The last thing is at the top of the dome is the critical point. Okay, so let's talk about what all these different things mean. So first, the triple line means solid, liquid, and vapor. All three exist in equilibrium. The critical point is the pressure and temperature above which you lose any distinction between liquids and vapors. So above which there's no distinction between liquids and vapors. And so when you get above the critical point, that stuff that you have that's not really a gas, not really a liquid, is called a superheated vapor. Sorry, supercritical. No, it's not called that. Supercritical fluid. So it's a fluid. It flows like a liquid or a gas, but it doesn't have the properties of either one. Saturated liquid means if you add a little bit more, so it's all liquid, but if you add more internal energy, it will start to boil, turn to vapor. And a saturated vapor is all vapor. But if you remove any energy, it will start to condense. Meaning turn to liquid. Okay, so as long as you're not above the critical point, if you're in a saturated liquid and you add energy, it'll enter this region. And if you keep adding energy, more and more of that liquid will turn to vapor. Like, I guess we're used to seeing water in this phase, like in a sauna or something, you know. And if you get, if you have saturated vapor, it's at the boiling point, but you start taking energy away, it'll start to condense. So at first you'll get some droplets of water, you'll still have mostly vapor, and little by little, all of that vapor, as you take energy away, you'll turn to liquid until you get back over this region. One more thing, the superheated vapor. That just means any vapor above its boiling point. And we're not very familiar, you know, in everyday life with superheated vapors, actually, even though, like, you know, we boil water all the time in the kitchen or whatever. But, you know, when you boil water, like you boil water on a teapot or something, you see the steam coming out. What you're seeing is, so the steam comes out as a vapor, but it's right at that saturation temperature. And so it's, as soon as it starts hitting air outside of the teapot, it's starting to condense. And what you're seeing is the air condensing as it comes out. So the only reason you see that you see steam is you're seeing it turn back into water, liquid water. But if you had the steam come out of the teapot into another vessel that heated it more, that it wouldn't be at 212 degrees anymore, you know, at our pressure. It wouldn't be at the boiling point anymore. Its temperature would start to increase. And at that point, if you let it come out into the air, you wouldn't see a cloud of steam. You wouldn't see anything because it would still have to be cooled down more before it started to condense. And so that's why, like, you can make superheated vapor in your kitchen, but it's sort of dangerous because you can't see it and it'll burn you really badly, you know. Anybody have any questions about that? That's all just sort of background. But really, for calculations, I'm going to show you. So in this picture of the projections of the PVT surface, it showed the pressure temperature projection and the pressure volume projection. I want to look at a pressure No, I want to look at a volume temperature projection. And I want to do that to talk about phase change. Okay, so let's look at the so we're going to look at the temperature specific volume diagram to understand what happens when phase changes. Okay. So this is what the diagram looks like. And if you look at the thick line, it's a picture of that vapor dome. So you have compressed liquid, the liquid region on the left. You have the saturated liquid on the left side of the line, critical point. And then on the right side of the line, you have saturated vapor and then superheated vapor. And to understand what material would do as you change the temperature. Okay, so let's think about holding the pressure constant, which is like this is what you're doing in the kitchen or something, so imagine we're just dealing with atmospheric pressure and we're changing the temperature of the material or adding heat to the material. So imagine like liquid water in a pan and you have a fire under the pan. So you're putting energy into the liquid water. And either one of these two lines will work. Those are just representing two different pressures. Okay, the higher pressure is up above, the lower pressure is below. The higher pressure is getting you closer to the critical point. But so what happens, you start with liquid over here, you add heat through the fire, and at first, before you get to that saturated liquid line, you get a big change in temperature of the water. That makes sense, right? Like you have a fire under the pan, it's changing the temperature of the water, and your experience with that. And also notice that relatively, and this isn't like numerically accurate, this is sort of a general picture, but notice that relatively, here versus over here, you get a pretty small change in the specific volume when you increase the temperature. Okay, so what that's saying is if you took a cup of water, measured it, put it in the pan, started heating up the water, before it gets to the boiling temperature, if you poured it back into the measuring cup, it would still be about a cup. The volume doesn't change very much. But then once you get up to the boiling temperature, now something different starts to happen. So right when you get to the saturated liquid at 212 degrees Fahrenheit, now you still have the fire under it, but if you had a thermometer in that liquid, you would not measure any change in temperature anymore for a long time. Okay, that water gets up to 212 degrees Fahrenheit. And from then on, what's happening is the water is just starting to boil. You're getting the start of the phase change. And molecularly, what happens is the water molecules are being forced to spread way apart, And so any heat you add to the saturated liquid at that point is just going to spreading out, pair by pair, spreading out these water molecules. And so the temperature stays at 212 degrees, but the volume gets, and now if the water starts to boil in a pan, it's hard to keep track of all the water, but if it's covered and somehow you still are controlling the pressure, it will get a little harder now. But now you're getting a huge, little by little, a huge change in the specific volume as the temperature stays the same. Until finally it's all steam, okay? You don't have any liquid water left. And at that point, if you keep heating it up, all of the vapor becomes superheated, and now it would take taking energy away in order to get it back into like a visible steam where it can condense again. Okay, so this is for refrigeration systems and heat pumps and power cycles. For all of those things that we're studying, this region in the middle is super crucial to understanding how that works. So this right here so let's say at a constant pressure, which is what we're looking at, there's a big energy difference between saturated liquid so does saturated liquid have low energy or high energy compared to saturated vapor? Low. And saturated vapor but there's no corresponding change in temperature. No corresponding temperature difference. Okay, so why is that important? This is a really useful thing in engineering systems. So that energy difference without a temperature difference is really useful. Because often energy is added through heat. Well, let's say added or removed through heat. Okay, so here's an example of how we'll take advantage of this, how engineers take advantage of this in a lot of cases. So imagine a normal gas at 70 degrees, Fahrenheit or whatever. So imagine a normal gas at room temperature. and imagine using heat to add or remove energy to or from this gas. So the key to what you're trying to do is you're trying to get as much energy out of this gas or as much energy into this gas as you can. So let's say you want to add energy to the gas. So how would you do that? You have the gas on the inside. It's at 70 degrees Fahrenheit. To add energy to the gas, you put a higher temperature on the outside, 71 degrees Fahrenheit. Okay. And then now that there's a difference in temperature, energy can flow through heat into the gas. Okay. But pretty quickly, you have this 1 degree temperature difference. Almost immediately, you get enough energy in there to raise the gas temperature to 71 or close enough to 71 that that flow pretty much stops, right? So as soon as the gas reaches 71 degrees, the flow of heat stops. Same idea with removing energy. So you have a gas here at 70 degrees. You want to get energy out of it, so you surround it with a lower temperature. Heat flows out of the gas into here, but as soon as the gas reaches 69 degrees, the heat flow stops. Okay. But now, let's say that, so let's do it with a material whose boiling condensing temperature is 70 degrees. Okay. And imagine the same thing. So here's the material. It's 70 degrees. So this is the one where we're trying to add energy. So we surround it with 71 degree atmosphere. And say that you start with this material as a saturated liquid. Okay. So what happens now? Heat flows in from here into here, but for a long time, it doesn't raise the temperature of the material. Okay. Your goal is to get as much energy through heat from here into here as you can. But if this is a saturated liquid to start with, it's still at 70 degrees. But like in the examples above, as soon as you started letting heat flow, this temperature started rising. Okay. If this is a saturated liquid, you start letting heat flow in here, all it's doing is changing it from a saturated liquid toward a saturated gas. And a huge amount of energy flows in before that process is complete. Okay? So a lot of energy flows in before the material temperature starts to rise. Because all you're doing is going from a saturated liquid toward a saturated vapor. And then if you're trying to remove energy, it's just a reverse process. So you have this material that's at 70 degrees. You have the surroundings at 69 degrees. You start with that material as a saturated vapor. And again, a lot of energy flows out of the material before the material temperature changes. So in that case, we'd be going from a saturated vapor to a saturated liquid. Okay, so when you're trying to choose a refrigerant for a air conditioning system or something, your choices of refrigerant are based on at your operating pressure and your operating temperatures. You're choosing a refrigerant that has its boiling condensing point right in your operating range, so that when you want to remove a ton of energy from something, you can go from a vapor to a liquid. When you want to add a ton of energy to something, you can go from a liquid back to a vapor. Okay, it's sort of the key reason that thermal energy is such a useful thing in engineering applications. It's used in diesel engines and gas engines, power cycles, turbines, air conditioning, refrigeration, all that stuff. Anybody have any questions about any of this? Yes. Yes. Right. The idea is you could use the same substance, you know. So yeah. So because of this, this is how the phase change works between liquid and vapor. If you keep adding heat to the material, first you're just raising the temperature of the liquid. Okay. Then you get to the saturated point, and at that point, look what happens to the the vertical is the temperature. So now we keep adding all this energy. We add a ton more heat, and the temperature stays constant through that whole process. Okay. So at this point, it's 70 degrees for the material on, this hypothetical material, and at this point, it's 70 degrees. But there's a gigantic difference in internal energy between this and this. Okay, so that's the idea of it. Gas has a lot more internal energy per kilogram or whatever per mass than liquid does, even at the same temperature. By the way, this, sorry, this is a little messy, but go over here to where I circled that amount of energy during the phase change. the amount of energy difference between the saturated liquid and the saturated vapor, called the latent heat. And it's called, the name latent heat makes sense if you think about that as all of this. Well, it's not really heat, so that part isn't quite accurate. It's internal energy. But the entire difference in internal energy between this point and this point, it doesn't show up in the temperature. If you're just trying to guess how much energy this material has based on measuring its temperature, you could be off by this much. And so if you have a saturated vapor, it's holding all this latent heat. It doesn't show up as temperature, but it's waiting there for you to use it to do work, you know. Yeah, you can, yes, these are still simple compressible substances. So if you know any two of those properties, that's good enough. So yeah, it's not like it's hard to measure, but I think the term latent, like it's waiting, like it doesn't show up, but it's waiting to do something. The idea is that it hasn't changed the temperature of the material, but it's still there waiting for you to sort of release it. That's the heat you can't measure with the thermometer, yeah. The energy you can't measure with a thermometer. In liquids or superheated gases, you measure the temperature. If you know the pressure, you measure the temperature, and you know the amount of internal energy. But that's not true when it's inside that vapor dome, when it's a mixed liquid gas. Oh, there's something about like this, basically the same kind of thing as you're going from a solid to a liquid too. You know, there's also latent heat. So why don't all these power cycles and refrigeration systems, why don't they ever go from a solid to a liquid? The same idea would work. And it just turns out that there's a lot, like I forget the multiple it is, but vastly more latent heat between saturated liquid and saturated vapor than there is between a saturated solid and a saturated liquid. So this is just the more efficient part of the material phase change process to use. Why don't we stop there? And I mean, anybody have any more questions? Okay, let's stop there, and I'll give you problems to work on that's sort of related to the stuff we did before this. And then on Thursday, we'll start talking about using property tables, and we'll get into, I can assign some more problems. And like I said, I think by the end of the day today, your test scores will be posted.